Hi there, welcome to the 41st episode of the Synth project, where we are building a synth together. Today we will work some more on the new MIDI module. We will add the capability of generating the control voltages for the notes and for the velocity, as well as generating the corresponding gate and trigger signals necessary to activate a number of the modules in the synth, some of which already implemented. Let's begin! Let's start by taking a look at the modifications to the schematic. In this picture, this section above is basically the part that we have seen in the previous episode, although in another format. It is basically the section that controls the liquid crystal display with the signals coming from this pin header and going through the two LLC devices that adjust the logic levels between the Arduino Duo and the 1602A LCD. Everything else is the new part. This single pin here, D24, is the one from which the gate signal comes from. We will see later how the signal is generated. What we need to know right now is that this is supposed to be a signal with 5V logic levels. However, since the Arduino Duo provides 3.3 logic levels, we need to convert the signal from D24 through one of the still available logic levels converters on LLC2. The signal that comes out of the converter goes directly to header H6, which is the one that connects to the front panel. Back to the left side of the schematic, we find header H11, which is the one that takes the power supply from the power rail of the synth rack. Further down, we have header H3, that connects to the DAC outputs of the Arduino Duo. Such DACs are those used to generate the control voltages for the notes and for the velocity. The important thing to note here is that the Arduino Duo DACs do not provide a range of voltages starting from 0 and going to 3.3V. Instead, they provide a range that goes from a minimum of 0.55V to a maximum of 2.75V. What we need instead is a range, really, that goes from 0V to 10.58V to be able to use the full range of notes made available by the MIDI protocol. So, to be able to use the Arduino internal DACs, we need to move the lower end of the range from 0.55V to 0V, and then we need to amplify the signal to translate the upper end to 10.58V. This is achieved by op-amp U1.1, which is part of an LM358. This op-amp acts simultaneously as a mixer and an amplifier. The mixer combines the signal coming from DAC 0 with a reference voltage of negative 0.55V, and this is to lower the beginning of the CV range to 0V. The mixing is done through resistors R3 and R5, both of 100K, so that their high resistance will not draw much current from DAC 0 and from the voltage reference of negative 0.55V, which comes from this little circuit at the bottom. In here, we take the minus 12V from the power supply coming from the power rails, and we stabilize its value to 2V using resistor R8 and the Zener diode D1. Capacitor C3 is used to shunt to ground any possible electric noise coming from the Zener diode, and the multi-turn input R7 takes care of extracting the exact voltage of negative 0.55V from the 2V reference created by the Zener. Since this input has a low value of 500 ohm and the resistor on the mixer is of 100K, the mixer will not affect the value of our reference voltage. Back to U1.1, you can see that the op-amp is also configured as a voltage amplifier having resistors R12, R11 and R10 in the negative feedback. These resistors are calculated to provide the exact CV range we need for the VCO that generates the notes. Note how the feedback resistor that brings part of the output voltage back to the inverting input is split in two different resistors in series. This is done to be able to obtain the exact amplification value that we need. The output of the op-amp, available on pin 1, goes directly to header H6 that provides the connections to the front panel. Let's now talk about the velocity CV. Since the velocity needs to generate a range of voltages similar to the one for the notes, so that it can fully control a VCA, the output of DAC 1 follows a similar path as the one at DAC 0, going through an identical circuit that modifies the range of the velocity control voltage. We do this through op-amp 1.2 and the resistors R4, R6, R9, R13 and R14. The output of the op-amp goes again directly to header H6 to become accessible on the front panel. The last part of the schematic refers to the generation of the trigger signal. The circuit is made of the two op-amps U2.1 and U2.2. The gate signal enters through capacitor C6 and generates a pulse every time the gate signal changes. This pulse is given to the voltage comparator made of U2.2 to make sure we don't create a pulse because of some noise on the gate signal. The level of the pulse at the output of the comparator will be either plus 12 volts or minus 12 volt. Resistor R16, along with the zener diode D3, takes care of cancelling the negative pulses and cutting the positive pulses to the required level of 5 volt. After that, the signal goes through the voltage follower made of op-amp U2.1, which is responsible for lowering the impedance so that the modules that receive signal do not affect its quality. The output of this last op-amp goes again to the pin header H6 to make it available on the front panel as the trigger signal. It is time now to take a look at the code that will make the circuit run. But before doing that, let's clarify some key points that will help explain how the code works. Let's start with the usage of the internal DACs of the Arduino. First, the Arduino Due has two DACs, named DAC 0 and DAC 1. We will use DAC 0 for generating the notes CV and the DAC 1 for generating the velocity CV. Both DACs can work at several resolutions, which we can set with a simple function call. Given the kind of output we expect, we will set the resolution to the max value, which is 12 bits. Second, a regular DAC is supposed to output from 0 volt to its max value that is dictated by the logic levels used. But it's not so for the Arduino Due. Instead of having a range that should be from 0 volt to 3.3 volt, the DACs on the Arduino Due have a range that goes from 0.55 volt to 2.75 volt. Moreover, we actually need a range that goes from 0 to over 10 volt. To satisfy our requirements, we need to do two things then. One, translate down the output voltages by those 0.55 volt, so the range will actually go from 0 volt to 2.2 volt. And two, we need to amplify the final output so the range can be actually extended from 0 volt to exactly 10.58 volt. We have seen already the circuitry necessary to do that in the schematic. However, our software will have to do one more thing, and that is the translation from the note numbers provided by the note-on MIDI messages to actual voltage values that the DAC circuitry will need to generate, along with the translation and the amplification of the output signal. Rather than doing a bunch of calculations every time a note CV needs to be generated, I made all those calculations offline and collected the results in an array that contains all the values for each MIDI note number. So, to obtain the value for a specific note number, we will just need to access the array with that number as an index. Finally, let's also talk a little about the velocity CV. From the hardware perspective, also this signal needs to be translated and amplified exactly like the note CV. However, we don't need to use an array to generate the numbers for the DAC, because the velocity value is supposed to be changed continuously and not in steps like with the notes. And therefore, to translate the number provided by the MIDI message into a number to drive the DAC, we just need to multiply the number from the message by a conversion factor that keeps into account the different range of the two sets of numbers. See, the thing is that the numbers coming from the MIDI messages go from 0 to 127, but the DAC needs to be controlled in the range that goes from 0 to 4097. So, to go from the first set of number to the second, we just need to multiply the MIDI number by 4097 and divide it by 127. That's all. And now let's take a look at the Arduino code changes in support of this new circuitry. The first thing to note is that I reused the code from the last episode and just added the new pieces to make the new features work. The added code is for the generation of the notes CV through the DAC 0, the generation of the velocity CV through the DAC 1, and the generation of the gate signals through the pin D24. There is no new code for the trigger signals, since those are generated directly from the gate signals through the added hardware we already reviewed. Let's go through the new code together. For the existing code, please refer to the previous episode. The link is coming out now on the upper right corner of this video. Here is the array I mentioned earlier. Each element of this array represents the value that we need to input to the DAC 0 to obtain the correct voltage for the note number we have received in the MIDI message. The note number itself is the index of the array. You may have already noticed that the array is written in such a way that each row of data represents a specific octave, identified in the comment on the side. We will use this table in just a moment, once we go through the changes of the note block callback function. These general constants provide information for the code to use later. Using such constants, in case we later need to change some of the values, we just do it here, and the rest of the code will use the new numbers automatically. The global variable active notes keeps track of how many notes are being played, which can happen if we receive a number of note-on messages without receiving any note-off message. We need to keep track of this number to be able to handle correctly the gate signal. The gate needs to go on as soon as the first note is played and needs to go off only after the last note is terminated. The handle not off callback function has a few new lines at the end of it. First, it checks if the number of active notes is greater than 0. If not, it decrements the count by 1 since we are turning off one note. After that, we actually turn off the note by forcing the control voltage output to 0 volt. Well, 0 volt is not actually no sound. In reality, it is the very first note that the VCO can play, but that will have to do. After all, it is going to be the gate signal that will actually silence the note's output once it goes off. And this is exactly what these last few instructions are for. We check if there is still any active note being played. If not, we turn off the gate signal by writing a logic 0 on the gate pin, which is currently D24, according to the definition of the constant gate pin that we already have seen above in the file. The handle not on callback function has also a few lines of code added to it at the end, plus a new variable defined at the very beginning. This new variable is named mapped velocity, and it is used to locally store the converted value of the velocity, which is the value that needs to be given to DAC 1 to generate the correct control voltage. The actual new code begins at line 145, where we increment the number of active notes, since we have a new note to play. Next, we do the conversion of the velocity value, using the constant velocity multiplier that was previously initialized to 4097 divided by 127. Follows the instruction to emit the note, the one to bring the gate signal to high, and finally the instruction to emit the velocity control voltage. There are also these few lines of code to print the generated information on the serial monitor, but this is just there for the padding. After that, we find the next change in the setup function. Here on line 226, we set the bit resolution of the two DACs. It is just one instruction for both DACs, since we cannot have different resolutions for the two of them. Follow the instructions to define the usage of the gate pin D24, as well as the two DACs, represented here with not CV for DAC 0 and velocity CV for DAC 1. Finally, the new global variable active notes is initialized to 0 since we are just starting the MIDI module, and of course we cannot have notes already playing at this time. Now that we have seen the new work on both the hardware and the software, let's move to the lab to see how I implemented the hardware changes and how they can be tested. The whole circuit is mounted on this platform that I made with my own 3D printer. There is space to position some breadboards, as well as other PCBs like the Arduino Due, and there is also a panel in the back with holes of 3 different diameters to attach various mechanical interfaces, for example, like in this case, potentiometers and jack sockets. Building our prototype on a similar platform helps us to reposition it on the benchtop or store it elsewhere while working on something else. All of that without the need to disassemble and reassemble the whole thing, or take the chance that some wire may get loose if we move the circuit with all the parts laying directly on the benchtop. Actually, I am glad I had this idea because it has proven very helpful. So, back to our project. The Arduino Duo is positioned in this slot of the platform along with a USB host shield attached to it. At this time, the shield is already connected to my Akai LPD8, and the code has been already uploaded to the Arduino. You can see that the Arduino has already gone through the initialization procedure, which was successfully completed as stated by the LCD contents. Visible on this small breadboard are the 2 logic level converters necessary to adapt the 3.3 logic of the Arduino Duo to the 5-volt logic of both the LCD and the Synth itself. A couple of words on this. As other people have noticed, I could have used a different kind of LCD, able to work as 3.3 volt and also capable of using the I2C serial protocol. But I already had this LCD model, and since I still need logic level conversion because of the needs of the Synth, and I also have plenty of digital ports available on the Arduino, it didn't seem necessary to go look for a different component to use. This breadboard on the bottom of the platform holds the new circuits built for the new features. On the left side we have this dual op-amp LM358 that handles the generation of the CV signals for the notes and for the velocity. This other IC on the right is also an LM358, and this one is used to handle the trigger signal, and it uses the circuit we examined earlier, which I also previously used to generate trigger signals for other modules of the Synth. The whole circuit is powered from 2 different sources right now. One is a dual power supply that powers the op-amp's circuitry, coming from this benchtop power supply unit. The other one is a 9-volt power brick that plugs directly on the Arduino. It is worth noting that this is only a temporary solution. The MIDI module will be powered directly from the power rails of the Synth rack, and the 9 volts needed for the Arduino will be locally derived from the plus 12 volt available on the corresponding rail. Here is the input to adjust the negative 0.55 volt necessary to translate the lower end of the notes and velocity control voltages. I have already made a rough adjustment, but you can see the current reference voltage of this voltmeter, and if I move the screw of the input, I can make a much more precise adjustment. I have also the oscilloscope currently connected to the 2 control voltage outputs. The right one is for the notes and the left one is for the velocity. We will now start the testing to see if the circuit works as expected. We will use the LPD8 to generate the test MIDI messages, and we will use the oscilloscope to see if the various signals are generated correctly. Right now, the yellow trace is the one representing the notes CV output, while the blue trace is the one representing the velocity CV. I'm now going to tap on one of the LPD8 pads, while we watch what happens to the control voltages on the oscilloscope. I will also be keeping my finger on the pad to prolong the note enough to be able to measure its details on the oscilloscope. Here I just tapped pad 1 and I left my finger on it. You can see that both the notes and the velocity CVs have been generated. The notes CV seems to be a little over 3.1 volt, while the velocity CV is about 10 volt, according to the scales I have set on the 2 oscilloscope channels. Now I will remove the finger from the pad, and the note CV has gone to 0 volt, while the velocity CV remained in the same value. And in fact, I have taken the decision to change the velocity only when a new note is present, and leave it unaltered otherwise. We will see later if this decision makes sense. If not, it will be easy to change the code to make it go away along with the note CV. Trying now with 2 different pads, one after another. and I also hit them with a different force to see if we obtain different values of both the notes and the velocity CVs. And that is exactly what happened. Now I am hitting the same pad several times, but with different forces. And yes, the signals look exactly what they are supposed to be. Let me move now the jack connectors to the gate and the trigger signals to see if they behave correctly as well. And yes, after hitting a pad, we see the gate signal going up and a short pulse on the trigger output. When releasing the pad instead, the gate signal goes down, and we have no further trigger signal as expected. Let's now play a little bit more with the pads to see if the signals follow up correctly, even though I play them quickly one after another. And again, everything seems to be fine. And this is all for this episode. In the next few episodes we will complete the design, the construction and the installation of the MIDI module in the synth. In particular, in the next episode we will concentrate on the control change messages, which are important to generate control voltages that can act on the various modules of the synth to control them from the MIDI device, rather than their own manual controls. Now, just a quick reminder for you to subscribe and to register for notifications if you haven't done so already, so you can be notified every time a new video is posted on this channel. See you in the next video, and as usual, happy experiments!